You ever feel like you're being interrogated? That's how I feel whenever I read the this problem. There's so many questions involved in it, and they're not really split up. So I'm going to split it up in some different parts. This one, we're going to begin with starting with this charge distribution, the figure A, I believe, in the textbook, where we have two charges, both of equal magnitude and both positive, a distance d from each other, and then midpoint between those at a distance z above the x-axis is a point P where we're trying to evaluate the potential. Now, typically, we would use this form for the potential, where we bring in a point from infinity and evaluate the E dot dl, the electric field along that line until we get to a certain point P, and we take those distances, and that's what we do with the in order to find the potential at that point. But we actually have a new tool now, because I guarantee if you try to set up this integral, it's gonna be very fun for you. So what we'll do is we'll go ahead and use this form for the electric potential, and this is only used for references that we pull out from infinity and bring them into a certain point to evaluate the electric potential at right here. And this was covered in the section, and this is the new set of problems that we're going to use to exercise this new way to get the potential for these charge distributions. So we can go ahead and use this one. The way this is different is where we basically just integrate over the charge distribution instead of integrating the electric field directly. And so when we're dealing with discrete charges, like just not a continuous charge distribution, but just chunks of charge that are sitting around, instead of an integral form, we just do a summation form. So this is a good exercise for that one. So instead of an integral, we just do the sum from 1 to n. This is just the general form. We just add up all the charges and then divide them by their distance from the point that we're trying to make. And then we have, for our specific version that we have here, it's going to be we have two charges, and the distance that each charge is from the point is going to be this one. And of course, we're going to dust off our geometry, and we know this is going to be the hypotenuse, so the square root of 1/2 d and then z. So we'll go ahead and write that explicitly. So z squared plus d over 2, quantity squared. And that is our electric potential at the point P. So that's a pretty quick way of doing things, a lot faster than doing this integral. Again, I highly encourage you just to set up that integral and see what I mean by that. So the next part of the million questions that's part of this problem is verifying that the electric field is in fact equal to the gradient of potential. And so the way we set it up is we'll go ahead and just do the gradient. And this far in the textbook, we've worked pretty far through all the gradients to know that it's essentially the partial in respect to each component of our potential. And so for the potential, I'm just going to go ahead and just copy and paste it here for time. There we go. And this points in the z-hat direction. Okay. Right, and so the reason why I did all these dots, because these are partials in respect to x and y, and there's no x or y's here, thanks to the symmetry here. So we'll go ahead and turn these into zeros, right? And just concentrate on this one right here. So this partial comes in and just only hits the 1 over the square root of all that stuff in there, and the constants move out. So we'll just go ahead and pull the constants out. So what do we have? We have a 2q, 4 pi epsilon naught. And then our integral is, let's see here, chain rule 1/2, right? And then we have a z squared. So it's amazing how calculus ends up getting easier whenever you start working on actually applying it, and ends up just becoming a kind of routine thing for you. So these minus signs cancel out. This 2 cancels out with this 1/2. Ooh, let's see here. We have a 2 here, and then that cancels out with this 4. What else? I think that's enough for now. So we'll take a step back. And let's see here. So we have a QZ over 2 pi epsilon naught. All right, and then we have our z squared plus d over 2 over 3 halves, pointing in the z hat direction. And if you go back and you check this out with the problem that they recommend to check it against in the back of the book, you'll find out that's actually in accordance with that one.